So our next speaker is Yichao Zhou of Duke and...
Hello, I'm from Shanghai University.
Oh, from Shanghai. Okay, sorry. What do I know? Go right ahead.
Good afternoon, everyone. I am Yichao Zhou from the Tsinghua University, and today I will introduce our recent work, an efficient parallel algorithm for accelerating computational protein design. Let's begin. The first problem is we know that the structure-based computational protein design provide a promising tool in a wide range of protein engineering applications, such as new drug discovery, drug resistance prediction, enzyme optimization, and new biosensor design. For example, the protein design can be applied to design a new anti-HIV drug to inhibit the entry of HIV virus to our...
Too tall for this equipment. Can you lean into the microphone?
Is that okay? Is that okay, that's much better. For example, the protein design can be applied to the design new anti-HIV drug to inhibit the entry of HIV virus to our human cell body. Here is a more formal definition about what is the structure-based computational protein design. The design algorithm tries to find a new amino acid sequence based on a known structure, such that the result energy of the molecule complex is minimized. In practice, assumptions are often made to decrease the complexity of the design algorithm. In many protein design models, the backbone of the protein is assumed as a rigid body, while the side chains of the protein are only to rotate among a finite set of discrete conformation, which is also called the rotamer library. Assuming the pairwise energy function, the discrete rotamer, and the rigid backbone, we can treat the protein design problem as an optimization problem. Here is the energy function for this problem. In the energy function, the E sub 1 is the self-energy for each rotamer, while the E sub 2 is the pairwise energy between two different rotamers. Okay, even with such assumptions, people still prove that this problem is an NP-hard problem. So many approximate algorithms, such as Monte Carlo brief propagation, has been proposed to solve it. However, this algorithm cannot give any provable guarantee that the global minimum energy conformation will be founded. On the other hand, exact algorithms, such as the combination of the dead-end elimination with A star, branch and bound, and the trick decomposition, can guarantee that the global minimum energy conformation, the optimal solution, will be outputted as the final solution. Among them, the dead-end elimination with A star is very popular. In this design strategy, the dead-end elimination is first applied to the search tree to prune some branches that are probably not in the final solution. Second, the A star algorithm is used to search over the remaining conformation space to find the global minimum energy conformation. Here is an example of 3 mutable residue protein search tree. The first residue has 3 allowed rotamer, while the second and the third residue has only 2. In the search tree, each layer we determine 1 rotamer for a particular residue. So in the last layer of the search tree, the whole protein will be determined. Finding the global minimum energy conformation is equivalent to find a node with minimum energy in the last layer of the search tree. This graph is almost the same as that in the previous slides, except that the shape of the rotamer is replaced by a number. This number is calculated by the function fx, which is also called a heuristic function in the A-star search algorithm. There are 2 parts for fx, the gx and hx. The gx is the energy that among the residue which has determined, while the hx is the lower bound of the energy which involves undetermined residue. For example, For the nodes that in the layer which is labeled with residue 2, the Gx is the energy between residue 1 and residue 2, while the Hx is the lower bound of the energy between residue pair 1, 3 and 2, 3. If the heuristic function is always smaller than the actual energy, we call this heuristic function admissible. If the heuristic function used in an A-star search algorithm is admissible, then it is guaranteed that the first solution A-star search found is the global minimum energy conformation. Here is a simple demo for what is the A-star search. Initially, we put the root in a data structure called a priority queue. So we will extract a node from the priority queue. We expand its first child, and we need to calculate the energy heuristic for this node. Then we push the node with its energy heuristic back to the priority queue. The second child for node X is proven by the dead-end elimination algorithm, so we can safely ignore it. The third node is just the same as the first node. We calculate its heuristic function value, and we push the value back to the priority queue. Okay, now there are two nodes in the priority queue. The A-star search algorithm will choose the one with minimum heuristic energy to start its second round of expansion. And this is the result of this expansion. And we will have 3 nodes in the priority queue. A-star search algorithm still uses the node with minimum energy heuristic and starts its next round of expansion. After expansion, we found that a node in the last layer of the search tree is being expanded. So since our heuristic function is admissible, we can guarantee that this node is the global minimum energy conformation. Okay, the combination of the dead-end elimination with A-star search algorithm can guarantee that the global minimum energy conformation will be founded. However, in the worst case, the A-star search algorithm still runs in exponential time. Thus, further optimization is needed. In our contribution, we optimize the calculation of the heuristic function. We design a new parallel algorithm which can do the A-star search on a GPU platform, and we use a memory-bounded strategy in the protein design problem. By combining all this optimization, we can finally achieve 20,000x speed up in our largest tested data. First, let me give a brief introduction about the concept of GPU computation, since we will use the GPU as our framework. The main difference between a CPU and a GPU lies in how they handling the computational task. A CPU usually contains several cores, which is highly optimized for sequential execution. On the other hand, a GPU usually contains thousands of cores, which is good at handling different tasks at the same time. So in order to bring the power of GPU into play, we need to modify our algorithm accordingly to utilize such high degree of the parallelism. The first question is, how can we parallelize the traditional A-star search algorithm? Well, the first step is very straightforward, based on the observation that the computation of the heuristic function is just a series of independent work which can be directly be parallelized. However, this algorithm has this problem. One reason is that the degree of the parallelism of this algorithm is determined by the number of nodes in the search tree, which is the number of rotamol for a particular residue in the protein design problem. This number is pretty small in real life, which is far smaller than the number of cores on a GPU. So this is not enough. How can we further increase the parallelism of this algorithm? One possible solution for this algorithm is that we may extract multiple nodes from the priority queue. By doing this, we will have more nodes waiting for the computation of a heuristic function value. Thus directly increase the degree of the parallelism. However, problems still exist. This time, the bottleneck of the whole algorithm becomes the priority queue. The reason is that we need to extract multiple nodes from the priority queue, and then we need to push back multiple nodes, many nodes back to the priority queue. We know that the priority queue is implemented by the binary heap, which is a sequential data structure, very hard to be parallelized efficiently. So how can we deal with this problem? Our final solution is that we can use multiple priority queue. In this demonstration, we will use 3 priority queue, which is operating independently. Initially, we will extract 3 nodes from the priority queue. Since we have 3 priority queue, this can be directly done in parallel. We can expand the child of nodes in a parallel fashion. We can compute the heuristic function value in a parallel fashion. And we can push the nodes back to the priority queue also in a parallel fashion. When we implement this algorithm, we also make sure that the node with same parent will be pushed back to a different priority queue to make the heuristic energy in the priority queue more even. Now we have optimized the A-star search algorithm a lot by the parallelization. However, the memory exhausted problem still prevent us from solving a large problem. Our idea to solve this problem is that we can just throw away some unpromising node. So when we run out of the memory, we first do a global sort according to the node's heuristic energy. Then we only keep the partial nodes with minimal heuristic function value. The benefit of this merge is obvious. We are able to continue to run the search algorithm, run the protein design problem after we run out of the memory. However, if we throw away some nodes in the middle of the A-star search algorithm, we cannot fully guarantee that the global minimum energy conformation will be founded. However, this algorithm still has its advantage compared to the traditional heuristic algorithms such as the Monte Carlo or brief propagation. First, it can guarantee that the global minimum energy conformation will be founded when our memory is large enough. Second, it is possible to know that the solution we got is the global minimum optimal solution or not by tracking the heuristic function value of the nodes that we throw away. Our experiment is based on the Osprey framework from Donald Lab in Duke University. We performed a native sequence recovery experiment on the crew redesign problem. We use our new A-star search algorithm with the IMIN-DEE, which is a very new dead-end elimination criteria, which is able to consider the continuous sidechain flexibility. In the experiment, we want to measure the speed and the memory consumption of our parallel A-star algorithm. And we also want to know how our parallel A-star algorithm perform when it is under different memory pressure. Our software is available on the GitHub as an open source software. Our experiment is performed on a NVIDIA-CUDA framework with 2,500 logic cores. This table gives the running time of different A-star search algorithm. The column labeled with Osprey shows the running time of the traditional A-star algorithm, which is implemented in the Osprey. The A-star 1, the column labeled with A-star 1 shows the running time of CPU-based A-star with our optimization of the heuristic function. The column labels with the GA-star shows the running time of GPU-based A-star with different number of the priority queue. In the highlight columns, gives the comparison about the optimization of the computation of heuristic function. You can see that our optimization is very effective. However, due to the time limitation, I cannot elaborate this merged in the talk, and the people who are interested may refer to our paper. And this row gives the 20,000x speed up. The original algorithm from Osprey runs in about 6 hours, while our fully parallelized GPU-based A-star algorithm can finish the same work in 1 second. This is really a huge improvement. And this plot gives the scalability of our GPU-based A-star search algorithm. The x-axis shows the size of the problem, which is represented by the number of nodes visited by the A-star algorithm. The y-axis, the speed up from pairization, shows the multiple of the speed up, comparing the CPU-based A-star and the parallel GPU-based A-star. So you can see that the larger the problem is, the more speed up our algorithm will have. Memory overhead, because our algorithm will extract multiple nodes from the priority queue. Our algorithm will generate much more nodes than the traditional A-star algorithm. However, from this plot, we know that we don't in fact need to worry about this problem very much. When the size of the problem is large enough, this memory overhead is negligible. Okay, finally, this table shows the experiment result of the native sequence recovery experiment. The highlighted row shows the number of nodes needed by the traditional A-star search algorithm, which is very close to 10 to the 7. When we impose a node limitation to the 10 to the 6, we found that our algorithm runs very well. We can assume that the global optimal solution will be founded, and our recovery ratio don't change. When we decrease the node limitation to the 10 to the 5, we found that we can still get the global optimal solution on all the PDBs. However, in some case, our algorithms are not confident that they are the global optimal. But the recovery ratio is just the same as the previous data set. When the node limitation down to the 10 to the 4, a very strict node limitation, our algorithm do not perform very well. The recovery ratio is dropped, and we cannot get the global optimal solution on many PDBs. However, such strict node limitation is very rare in practice, because we will always use all available memory when designing the protein. This is only for evaluation purpose, and it will tell us that finding the global optimal solution is very important. It may affect the recovery ratio very much. Okay, in conclusion, our contribution include optimization computation of the heuristic function. We design a variant of A-star search algorithm, which is efficiently executed on a GPU platform, and we use the idea that we can design a memory-bounded search algorithm for the protein design problem. As a result, we achieve 20,000x speedups in the native sequence recovery experiment, and we are able to use only about 1/10 of the memory compared to the traditional A-star algorithm, while guarantee that the global minimum energy conformation will be founded. Our future work including testing on more affordable GPUs, or we can put our parallel algorithm to the large CPU and GPU clusters to solve a more large problem. And then we may pairize in the other part of the framework. Acknowledgement. I thank people from the Duke University, Mr. Kyle, Mr. Mark, and Mr. Pablo. And I thank people from Tsinghua University, Mr. Pu Fan and Mr. Chiwei. Here is the founding information. Thank you.
So it's a useful piece of software that, do you have it written in a generic framework that you could imagine there are other problems beyond protein design which could be mapped to an A-star framework? Is the GitHub code written in such a way that you could fit other problems, or is it very specific to the protein design?
In general, this A-star parallel algorithm is very genetic. You can do many things, but the one thing very special is that in A-star search, the computation of the heuristic function will consuming a lot of time. So when we design this parallel A-star search algorithm, it will use this feature, so it can be executed in a very efficient way. Yes.
Okay, thanks. So one more quick question: when you're porting into larger CPU clusters, do you think you would have problems kind of resolving it into smaller nodes, because you have more overhead between the communications of the different CPUs, right?
Yeah, I think we think about this problem, and I think the probability is very well, because our algorithm include multiple of the priority queue, right? Each priority queue is an independent data structure, so we can run multiple priority queue on different nodes, and it don't require much communication between them. Okay, thank you for your question.
Thanks for the talk. I'm actually using Osprey a lot to redesign the proteins. But do you have any special examples? You know, this can be, really applied in practice. Because it sounds like 6 hours to 1 second, and if there's a limitation, I would choose 6 hours.
I think this algorithm do not have limitation. We just design a drop-in replacement for the A-star algorithm implemented in the Osprey framework. So if you have a GPU, you can just download the patches from the GitHub and apply it, and it will directly accelerate the protein sample process. You can use all the feature provided by the Osprey. Is that your question?
No, it looks like the next slide. Yeah, here it looks like there's some sort of limitation.
Okay. This slide gives the problem, gives the experiment about the memory bounded parallel A-star search algorithm. It means that if you design a very large protein, then the traditional algorithm provided by the Osprey cannot finish it because it will run out of your memory. And one of our contributions is that we design a new method which tries to alleviate this problem by throwing some nodes in the design process. If your protein is not such big, if your protein can be designed on original Osprey, it can also be solved by the new parallel A-star search algorithm without any rules.
So it's a practical question: is how difficult it is to use? I'm already a user, and is it difficult to get used to new version of GPU?
The main problem is that you need to create a platform. If you use an NVIDIA GPU or AMD GPU, it is okay to use it. Maybe you need some configuration.
Because the Osprey 1 and the 2, there's like the big jump, and it changed a lot, and there was a sort of problem
just
before.
Download the source code and compare it. It just runs exactly the same as the previous.
Okay.
Yeah.
Thanks.
Thank you for your presentation. My question is not directly related to your method, but it's a rather trivial question.
Yeah.
So at the beginning of your presentation, you mentioned that this energy optimization problem is NP hard.
Yes.
And I'm wondering which NP complete problem that it can be reduced to.
If it is NP hard problem, then first the NP hard problem is a decidable problem. It will output you may confuse the concept of NP hard with NP complete.
Yeah, so in order to show that it's NP hard, you should reduce it to an NP complete problem.
Yes.
So I was wondering, which NP complete problem it can be reduced to, if you can remember it at the top of your head.
I cannot remember it, but in principle, it can be reduced to any NP complete problem since it is NP hard. I cannot give a proof in this presentation, but when I prepare this paper, there is a paper to prove this problem, which is NP hard.
Corresponding also of this paper. So if I remember correctly, the original proof of this NP hard problem I remember it's written in Protein Science in 1906, which is reduced from the suicide problem. Suicide, right? Yeah. Okay.
I have a couple of questions. So this is a good slide for the first one. You're discarding
Yes.
But when you look at the rotamers, there are clearly combinations, stay with me.
Okay.
There are clearly combinations of rotamer positions that are not allowable, right?
You mean static clash? Yes.
So have you are you thinking about incorporating such combinations earlier so that you keep the search space smaller?
And I think that's applicable. Our algorithm, our algorithm is guided by the heuristic function. In fact, it has already considered partial of the situation that you have described, because if some root modes will likely to crash, their heuristic function value will be very bad, so we will throw them first, throw away them in a very early stage.
Well, part of why I'm suggesting this is because then, as you go further down in the processing part, you could use a branch and bound algorithm. You're already using a threshold, right?
Yeah.
To discard things. So if you bring that threshold up higher into the computation, you have a branch and bound, and together with discarding unreasonable combinations, you might speed it up further.
Yes. Thanks for
Another
suggestion.
question now.
Yeah.
Go forward in the
Go forward.
spots.
Sorry. Forward, 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 forward.
There.
Yeah, this plot.
That one and the next one. What's going on around 10 to the 5th? Why do you get that bump, the dip and the wiggle?
We test many we use many testing data in our experiment. In fact, this is on a log plot if you find it in the x-axis, and the running time, in fact, is not very stable. So I think this is very common situation, because for the same design, for the same size of problem, we may run in different time.
There.
Yes.
There. Look at the next slide.
Next slide.
Next slide.
Next.
I think so. Yep. Yep. There.
In fact, the main reason which constructs this gaggle is that there are more nodes in this region. You find most of our test data drop in this 10 to the 5 region, so it will causing this artifact. It's just a wave, like.
Yeah, it's weird.
Yeah.
So one way to address that would be if you could permute the order in which you do the computation, sorry, and then see if you get the same bump and wiggle.
Yeah, this is the memory overhead. The memory overhead is a fixed value. So if you run your experiment multiple times, you will get the same table.
But what happens if you do the computation from the carboxy terminus and not the amino terminus? See what I mean? Just flip it around.
Okay, in fact, the one point on this table is just an experiment. In fact, you can get 2 points vertically if they have the exactly same size of problem, but with different running time. So this is just the error of the experiment.
So can I just make a comment on this question? So we did test on different proteins, and different proteins after the DE pruning, you may get to different situation or the remaining rotamers. Maybe that's the reason that this situation happened. But we are not sure. Yeah, it could be just a guess. Yeah. Thanks for your question. Yeah.